backside. From the sustainability, now we are changing to a different topic altogether, PVC. So you are welcome to this presentation on misconception and reality related to PVC and its process. Friends, before going to the misconceptions, let us first understand what we already know about PVC. We know that PVC is a polymer manufactured from vinyl chloride monomers, where M represents the degree of polymerization, which varies from 500 to 1500, corresponding to K value 55 to 70. Now K value represents average chain length or average molecular weight, and in turn the viscosity during processing of PVC. PVC, friends, is the only commodity plastic that contains 56.8% inorganic content, chlorine, that provides polarity, rigidity, and fire resistance to PVC. PVC is also a thermoplastic and it can be recycled many times. We also know that PVC is engineering plastics and its modulus of elasticity is comparable with that of polycarbonate, nylon, and polyester. PVC, friends, is 92 to 97% amorphous polymer, having a glass transition temperature of 80 degrees Celsius, and it has only 3 to 8% crystalline structure, having a wide melting point of 105 to 150 degrees Celsius, and this variation in the melting point is due to irregularities in the structure and in size of the crystallines. We know that higher the K value, higher is the crystallinity, and we also know that PVC cannot be processed without compound. Besides, there are drawbacks to PVC. During processing, PVC undergoes thermal and oxidative degradation. We also know that it undergoes UV degradation when exposed to solar radiation, and it becomes brittle at the lower temperature. This is all we know about PVC. However, PVC is the most researched polymer in terms of additives that mitigates all its disadvantages. As a result, PVC has emerged as a safe, versatile, and one of the cheapest commodity polymers, enjoying 30% market share. The estimated CAGR for 2025 to 30 is 7.22%. Indicating an impressive growth potential befitting the today's theme of the seminar. Besides, it requires 30% less energy during its production. No wonder PVC is said to be a 21st century
visibility decrease करा था थोड़ा इसको adjust कर लो.
this is what we know about PVC. But PVC is different from other plastics in many aspects. Its morphology, its rheology, during polymerization, during mixing, and during processing is 180 degrees opposite to other plastics in many aspects. No wonder its technology is known as PVC technology rather than plastic technology. And during PVC processing, it is only the 3 to 8% crystallinity present in suspension PVC that governs the processing and product quality rather than 92 to 97% amorphous part. Hence, as per the modern way of thinking, PVC is said to be processed within its crystalline melting range of 105 to 150 degrees rather than processing like an amorphous plastic, which as a rule of thumb is processed at glass condition temperature plus 100 degrees Celsius. Friends, this is a disruptive idea in processing of plastic, and lack of understanding about the different nature of PVC has given rise to many misconceptions and myths about its process. So let us unfold some of the misconceptions and look at the reality. The first misconception is that suspension PVC from any source is not much different. Friends, as we receive the suspension PVC, it has varying chemical irregularities like labile chlorine, unusual end groups, chromophores, traces of catalyst, initiator, etc. These are responsible for its thermal and oxidative and UV degradation, but unfortunately, it is not mentioned in any test certificate or certificate of analysis. The extent of stability varies from source to source and batch to batch. When we talk about source to source, I would like to compare with the cousins from the same family having same age. And when we talk about the batch to batch variation, it can be compared with the twins from the same parents. So such is the difference between the batch to batch and source to source. Now for the same K value, PVC from different sources also differ in physical properties like porosity, particle size distribution, bulk density, fish eyes, and so on and so forth. Besides, the source can be from acetylene or ethylene based. And when that comes, the acetylene-based PVC, usually coming from China, has the wider K value range, lower thermal stability, more impurities, and more fish eyes than the ethylene-based PVC. And of course, the additives are meant to overcome these irregularities and make processing smoother, cheaper, consistent, and quality-oriented. It is desirable that the processors are aware about such irregularities in PVC through simple lab testing. The second myth, friends, for the same K value resin, same formulation should be used. Now let us take example of case 57 resin that is used for injection molding. Here, what matters is the injectability of the compound during process. Now if you consider the formula resin grade B57, when we heard here B57, we normally think that its K value is 57, but in reality its K value varies from 54 to 56, as against the Rayon PVC, where the K value varies from 56 to 58. Yes, at some point of time, their K values overlap each other. But if we consider the minimum and maximum difference between the two grades, it is quite large. And the viscosity, shear heating, and the injectability of such material can only be modulated through a judicious combination of lubricants and anti-degradants. And it is beneficial, therefore, to check the K value of incoming PVC to get rid of these problems. The third myth, when we buy PVC from reputed companies, why to test them? Because most of the PVC processing industry do not test it and end up with irreversible problems. So due to short supply, we need to buy PVC from different sources. We continue with the K57 resin supplied by different manufacturers. It has K value of 57 plus or minus 1 that is mentioned in their test certificate. This means that the K value varies from 56 to 58 from different suppliers. But in reality, it can vary from 55.6 to 58.4, and this is due to the rounding off effect. From the literature we know, friends, that UPVC melt viscosity at processing temperature is exponential, that is molecular weight raised to the power 3.4. And if we replace the molecular weight with the K value, we get K value raised to the power 3.4. Now if we fill this K value with 56, we get this number, and if we fill it with the 58, we get this number. Now look at the difference in the viscosity between K56 and K58 resins. It is almost 12.87%. And if we replace 55.6 and 58.4 respectively, the viscosity difference is 17.74%. This viscosity difference actually makes problem during the injection, in the injection molding process for the fittings or other problems. Now, if we have a vaccine where the fluid viscosity is less, then we don't feel any pain while taking the injection. But when the viscosity is more, we get the pain. And the same pain, friends, is felt when the injection molding is taking place and material is getting injected. Therefore, testing PVC for K value, adjusting lubricants accordingly is always beneficial to achieve consistency in processing and the product quality. The next myth is for consistency, we must use a standard formulation. Majority of the industry use standard formulation, they don't change the formulation. So, a standard formulation is like a ready-made garment, and it is too loose for some people or it is too tight for some people. Does it mean, friends, that whenever PVC or additives are changed, we need to modify the formulation to get the best quality products? The logical answer is yes. It is hard. The recipe needs to be tailor-made based on the variation in the characteristics of the incoming PVC, the characteristics of the additives, and the type and condition of the processing equipment, especially the screw and barrel condition and the gap between them. A formulation, therefore, copied from other industries or copied from book does not work effectively. A standard formulation will give average results and may fail in some of the tests. The truth is that there is nothing like a standard formulation in the field of PVC. No two industries across the globe, by and large, use same formulation. And therefore, this is very, very important point I am putting forward here, that it involves two strategies. The first strategy, which is the popular, compromising and hard, is that use a standard recipe, play with the parameters, and this parameters is changed by the operator. Consider that there are 10 extruders in an industry. That means for the 3 shifts there are 30 operators, and 30 operators will change the parameter according to their own wisdom. Now this will result in an inconsistent product in industry. But the second and more logical way is specific, efficient, effective and smart way is to modify the recipe based on our experience, based on the test results, and to keep the same parameter, only changes within the normal changes that is required, plus minus 5 degrees, we get a consistent product, and you can improvise further on these particular things. So the second method appears to be a cost-effective method with little efforts we have to take. Now we move on to compounding. Many people feel that compounding is just a blending of PVC additives. Friends, people take PVC, add additives, blend it, and a compound is formed for them. And for this, they think it is a simple process. They use casual laborers. But friends, 90% of the irreversible problems related to processing and quality of PVC products are attributed to the improper mixing process here. So, in reality, the mixing process is a 3-stage process. First, testing, formulating, and mixing. During testing, it is advisable to test incoming PVC for K value and its thermal stability. During formulating, we decide what to add, why to add, which grade to add, and how much to add. And during mixing, we decide when to add, where to add, and how to add. This together forms SOP for the mixing process. And we have all these things together. It addresses 5 W's and 2 H's, but these are to be decided or defined by the quality assurance process owner to get rid of the 90% of the irreversible problems which are caused because using casuals and putting everything together. So this thing actually is a value-adding activity that needs to be done during processing in the PVC processing industry. Again, during this three-stage process, where do we focus? So during formulation, the formulator or the compounder must first focus on the properties required in the finished product. So he must look at what properties are required and where the product is going to perform. Then comes the processability on a given machine. Not all machines are same, and compound cannot run in a similar way on different machines. And then the price, of course, it has to be the lowest as possible without compromising quality. So we are addressing here 3 P's. Then during mixing, the diffusion of the polar additives and distribution of additives and dispersion of additives, that constitute 3 D's need to be addressed. Again, there should not be batch-to-batch variation between the 2 batches. So the bulk density of the material which is coming out from different batches must be uniform. And therefore, to control these, we must control the time of addition, the temperature of addition, the drop temperature, and the torque at which we are adding different additives. So these constitute 3 T's. Thus, we have 3 P's, 3 D's, and 3 T's to be addressed during mixing. Now, for the 3 consecutive batches of mixing, the difference in the cycle time should be less than 10 seconds to get a consistent product. So when we plot a time versus temperature graph for the 3 consecutive batches, the graphs must superimpose over each other. Likewise, when we plot a graph of time versus torque for the 3 consecutive batches, it must superimpose, indicating that the batches are consistent. During mixing, processing, the processes involved are adsorption, absorption, and coating of additives, and together with diffusion, distribution, and dispersion. So this constitutes the mixing process. Incidentally, PVC grains do not break during mixing because when the temperature crosses its last transition temperature of 80 degrees, it becomes softer and softer, and in turn, its shape becomes spherical. It behaves like a rubber ball. And because of the spherical shape, the bulk density increases. It follows that higher the temperature and higher the mixing time, higher will be the bulk density, and in turn, higher will be the output. It means through extruders. Friends, each grain of PVC should contain equal amount of additives like a multivitamin, tablets, or capsules, and the material should be free-flowing without formation of beads in this particular way. So, we are shifting now during processing. PVC melt flow is in the form of chains. We all know that polymers are in the form of chains. So, when we talk about the crystalline polymers like high-density polyethylene, it melts during processing. When we talk about amorphous polymers like polystyrene, it becomes softer and softer beyond its last transition temperature till it is processable. So at that temperature, as a rule of thumb, is last transition plus 100 degrees. But whether it is crystalline polymer or it is amorphous polymer, their flow is molecular. And in contrast, structure of suspension PVC is particulate. So when we open a bag of PVC, we see white grains like this one, whose grain size varies from 90 to 250 micron, and these are called the secondary particles. The white color, what we see here, is actually a skin, which is a porous and elastic skin. It is technically known as pericellular membrane, and its thickness is 0.2 to 1 micron size. This skin is a graft copolymer of vinyl chloride and suspending agent, and this suspending agent usually is polyvinyl alcohol. So the skin does not get destroyed during mixing process, during the intensive mixing process. This skin actually envelopes subgrains of 30 micron size, and according to Dr. James Summer, these subgrains also have skin. So we can correlate it with something like pomegranate, where there is a skin. You can see there's something like subgrains here, and inside that also there is some material. So, when we look at the PVC, when you remove the skin, you see this particular particular structure which has porosity within it. Now, these subgrains also consist of agglomerate that has the size of 10 micron, and these agglomerates are made up of 1 micron size primary particles. So suspension PVC grain is a structure built upon a structure. Now the question is, where are the PVC chains? Because normally we understand that when we talk about polymer, we talk about polymer chains. But here we are not talking about chains. So where are the chains? These chains are jumbled within primary particle that has a 1 micron size. And how many chains are there? 7 to 10 million chains, depending on the K value, are jumbled and encased within the primary particles, and they are held by crystallized. So I would like to compare it with a cotton ball, small cotton ball, where cotton fiber represents PVC chains and they are jumbled together, but the other end of the fibers is held by the cotton seeds that behave like a crystallized. To go into detail, let us see that the flow unit for PVC is 1 micron size primary particle, not molecules like other plastics. So I would like to take you at the nano level now. So this is a 1 micron size primary particle, and it contains many crystallites melting at 105 to 250 degrees Celsius. When we talk about the crystallites, it is like a disc shape having a thickness of 0.7 nanometer and major and minor axis of 4.1 nanometer. And friends, within this 1 micron primary particles, there are 7 to 10 million PVC chains. They are jumbled together or held by these crystallites. The length of the straight chain length of K67 resin is almost 233 nanometers. The distance between the two crystallites is 10 nanometers, and friends, we are now talking at the nano level. And therefore, understanding PVC at nano level and modifying its architecture during processing results in wonders and miracles in PVC quality. So the question is, why the millions of PVC chains do not come out completely during processing, and why it behaves like a particular structure? To understand this, I would like you to look at this red PVC chain. It is passing through this crystallite, which is melting at 105 degrees Celsius. It then passes through another crystallite having 190 degrees melting point. Then it may pass to 250 degrees Celsius crystallite. That means one chain is a part of many crystallites. And in every crystallite there are many chains. So this kind of interlocking of chains together with their jumbled nature prevents PVC chains to emerge out of primary particles unless these crystallites melt. So crystallite must melt, and they melt according to their respective melting points during processing. So in this way, actually crystallites, though they are only 3 to 7%, they govern the processing. To understand how they govern the processing, UPVC is processed at 180 to 190 degrees Celsius, and they hold the crystallites above 190 degrees do not melt. They hold the other chain, end of the chains, and do not allow the chains to come out of the primary particles. This is how the crystallites govern the PVC processing. Now, yet another aspect, what exits from the die is a PVC melt. This is what we understand. So PVC grains, when they enter into the feed zone of the extruder, under the influence of heat and shear, first the skin is torn apart, and then a hierarchical particular structure is exposed that further undergoes dispersion to generate a particulate flow here. So PVC, when it exits from the die, it is actually a three-dimensional network of primary particles which is 1 micron size. So The melting temperature for crystallites is 105 to 250 degrees, but the processing temperature is only 180 to 190 degrees, and therefore processing temperature is below the melting temperature of PVC. What does it mean? Does it mean that PVC does not melt during processing? The answer is yes. PVC does not melt during processing, but it undergoes fusion at primary particle level. So, this fusion undergoes at primary particle level of 1 micron. The process of interconnecting 1 micron primary particle is called fusion. Now, what does this fusion do? Fusion controls the mechanical property. If you look at this particular graph, as the fusion increases, the two properties, the first, the tensile strength increases continuously and then settles down. But when we talk about the impact strength, it passes through a maximum and then comes down. So, there is the optimum fusion of 65 to 70%, which is the best combination of rigidity and toughness. Now further, can we improve it without adding impact modifier and processing aid? This is the question. The answer is yes, we can improve it. How we can improve it? By optimizing the reversion percent. So it is observed that at a particular reversion, the impact strength suddenly skyrockets. So we have to capture that reversion percentage in our during the processing. And hello. The eighth myth is that fusion takes place in a single stage. Hello. Hello, yeah, thank you. So another misconception is that fusion takes place in a single stage. In reality, fusion takes place in 3 stages and not in single stage. In the first stage of fusion, if the external lubricants are more, then also the dispersion of 290 to 250 microns to 1 micron will not take place. Now, as the material proceeds from in the extruder ahead, the temperature increases, the crystallites melt according to their respective melting points, and the chains are released. These chains, friends, under the influence of counter-rotating extruder, they intermix, and what we call is the entanglement. This is the second stage of fusion. As the material comes out of the die, recrystallization may take place depending on the mode of cooling. When it is quenching like pipe, no recrystallization takes place. But if it is annealing, recrystallization takes place. Now there are 2 types of crystal. The first crystals that comes with the polymerized PVC, which is well within the primary particle. And then second crystal is formed within the entangled mass here outside the primary particle. So this is called secondary crystals. And when the sum total of primary and secondary crystal is maximum, we get the maximum tensile strength. And what DSC, differential scanning calorimetry, actually measures is the extent of melted and unmelted crystallites, and then it estimates the fusion percentage. The 9th and most important for the PVC process is how much filler we can add. So this is the model of the fused PVC. Now this free space here in between the primary particle, this is where titanium dioxide particles and calcium carbonate particle actually fills in. So if these particles are occupied within the this free space available, now suppose this particle is bigger, then what happens? And if quantity is more, then what happens? You can see on the screen here. Actually, because of the calcium carbonate particles, it deprives PVC chains from getting entangled, and this hinders fusion. This is the reason why the tensile strength and the impact strength goes down. Bigger the particle size, more difficult will be the fusion. Higher the PHR level, lesser will be the tensile strength and impact strength. So 8 PHR level is adjusted to be optimum. Now why people add calcium carbonate? they add calcium carbonate under the pretext that they are reducing the cost. Sorry, big sorry. If they calculate the costing, they will come to conclusion that it is not so. Why? Because more the quantity, more is the tendency to cause wear and tear in the extruder. As the wear and tear increases, the output reduces. If you increase more calcium carbonate, viscosity increases. The residence time of the material in the extruder increases. Therefore, you have to add more thermal stabilizer. So cost of the compound increases, and then the cost of production reduces because you produce less number of pipes. Pipes are not sold on the weight basis, they are sold on the meter basis. So if you produce less number of pipes, then you calculate whether adding more calcium carbonate is beneficial or not. Incidentally, impact strength is inversely proportional to the filler size of the particle, but when you reduce the particle size, the cost of calcium carbonate increases exponentially also. So, the 10th slide or misconception is that with the increase in temperature, viscosity of PVC reduces. Now when we talk about different polymers and when we heat it, then it melts or it becomes softer and viscosity reduces because their flow is molecular. This is true. But in case of PVC, the flow is particulate. And therefore, what Michael Unolt and co-workers reported that for UPVC, when the temperature is increased from 162 or 210 degrees, that is within the processing range of UPVC, the viscosity increases, does not reduce. And many people increase the temperature under the pretext they want to reduce the viscosity, increase the flow. That is not the case. The viscosity increases. The question is, why viscosity increases? Because PVC undergoes fusion. And this is the rarity and contradiction in the thermoplastic world, that on heating, the viscosity of PVC increases as against the reduction in viscosity of other polymers. So, because this sort of entanglement is taking place, and then more and more temperature will melt more and more crystallized, more chains will come out, and it will become more viscous. So this is the reason. So we must understand one thing, that while fusion increases mechanical strength, the degradation reduces it, and both occur at the processing temperature. And therefore, the mantra is to optimize fusion to 65 to 70% and minimize degradation as much as possible. Friends, this is the last slide I am presenting before you, that many people feel that they must increase the temperature of the die to get the fluidity of PVC within the die. Now, fusion should be optimum of 65 to 70% before plasticated PVC enters into die. We know that one. The fact, this is another very, very big mistake people are doing, those who are processing. Most of the people, they record temperature of the barrel zone 1, 2, 3, die zone 1 and 2, 3, etc., etc. Friends, we are processing PVC, and therefore what matters is the temperature of PVC and not the temperature of the barrel. Yes, barrel is a means to provide heat, but PVC does not receive heat only from barrel, it receives from frictional heat, from the screw also it receives. So this is one of the misconceptions. Now when we look at the profile here, this is the vacuum port where temperature should be around 150 degrees of PVC. As the material process further, here the fusion is taking place in this region. So for this, as a rule of thumb, the temperature before the material enters the die should be 180 to 190 degrees. And how to measure it? This is captured by melt temperature sensors. Many people do not understand why melt temperature sensor is given in the extruder. So this is the purpose. Also, when material comes out of the die, again its temperature should also be 180 to 190 degrees Celsius. Why it is so? Because the operator cannot judge the temperature of the material coming out, and therefore we use this infrared temperature indicator to judge the temperature. The point I am trying to make here is that the material entering the die should be at 180 to 190 degrees. The material exiting the die should also be at 180 to 190 degrees. Why? And therefore, the purpose of the die heater is only to maintain the temperature of the input of the PVC at 180 to 190 degrees and not to heat. This is to prevent overfusion, because as the fusion increases, then the impact strength reduces. So, when this happens, to help the pipe and profile to pass in methyl chloride test, it will give 0.000% failure results, indicating a uniform fusion across the different layers of the pipe, and you get pipe in this way. The last point which I want to make is that when PVC degrades, it forms conjugated double bonds on its color and discolors PVC. Irony is that human eye cannot detect up to 7 conjugated double bonds, and that are responsible for the UV degradation. So conjugated double bonds formed during processing provides a platform to the pipes or profiles or window profiles for the UV degradation when it is exposed to solar radiation here. So if we have the UV torch here, that is a way to decide, to find out conjugated double bonds up to 2, 3 or 4. So we should use this to improve the quality. And with this, I would like to end with the couplet, अगर धूल जमी है चेहरे पर तो आईना साफ करना नहीं, PVC प्रोसेसिंग करते समय जो गलतियां हमने डिस्कस की है वही दोहराना नहीं. With this I come to an end. Thank you.